Hi, good afternoon, guys. Today, we have two exciting topics, automated machine learning and hyperparameter tuning. These two capabilities in Azure machine learning improve the productivity and the time it takes to build a machine learning model. In Azure, we have several offerings under AI. Cognitive services, which are SaaS services that provide REST API. You can integrate those easily with your line of business applications. Now, if you want to build your own models, we have set of tools and infrastructure under Azure Machine Learning. Automated machine learning and hyperparameter tuning fall under Azure Machine Learning. So, how many of you have built at least one machine learning model using Python? Can you raise your hands? That's a good number. What you get out of this session is I'll go through really quickly the basics of machine learning model building. What is automated ML, how it works. I have a demo. What I'm hoping is at the end of this session, you should be able to build a machine learning model really in less than a day. Especially if you haven't built any models, you should do it in less than a day using automated ML. Let's start with machine learning and why machine learning, right? Machine learning has a wide range of applications from predictive maintenance. If you're working for a manufacturing company, you know if a machine goes down, your whole assembly line gets shut down. That is a huge loss of money for your company. Machine learning is being used to predict when a machine likely going to go down and proactively take steps and rectify it so that your assembly line keeps continuing. In fact, in Azure, we actually use predictive maintenance to predict when a server or hardware failure happens so that we can keep our Azure cloud running and your applications running. Right? If you have e-commerce offering, you know you can personalize your offerings using machine learning recommendations. Right? We have seen our customers increasing their revenue by double digits by using machine learning recommendation service. So there are lots of wide-ranging applications. Microsoft's goal is to infuse AI in every application and product we sell. You should be able to do the same by leveraging all the power that you have in your data that's hidden and machine learning. Let's start with a classic use case. In olden days, we used to write letters and stuff them in envelopes, write address, and mail it. Right? US Postal Service processes billions of these letters. Right? So they started with rules-based programming to actually process the address. The programs were very fragile and brittle, very error-prone. You change something, it breaks. So lots of envelopes are being manually processed because of the rules-based. In early 90s, they switched to machine learning. And let's see how this works. And they've seen dramatic improvement with machine learning systems. A typical machine learning system, you start with the data. So on the left-hand side, you have handwritten digits. On the right-hand side, you identify what those digits are. This is called labeling process. Right? This is the data that you feed into machine learning system and make the machine learn about your data. Right? Feed that into machine learning system. Machine learning has an algorithm and hyperparameters. Right? We'll go into more details on what those are. When you feed into machine learning system, the output would be a machine learning model. In this case, a digit classifier, right? Because it's classifying a digit, whether it's 0 through 1 to 2 up to 10, up to 9, right? So the model, the digit classifier here, you feed a new data. For example, handwritten number 2, and the classifier of the model predicts what the digit is, which is 2, right? What do you need to build a machine learning model, right? So you start with data. By the way, the better and high quality data set that you have, the better the model is going to be. And you have a training algorithm. These algorithms, you get lots of several choices depending upon the type of machine learning problem. Each of those algorithms have hyperparameters that you need to tune. Use the machine learning model training infrastructure, any compute, cloud compute, or local computer. The output is a machine learning model you can deploy or integrate into your line of business applications to start doing the predictions. Let's take a sample, just a binary classification algorithms, right? So you have many choices of what these algorithms are. Some subset is shown here. There is a SVM, support vector machine, decision trees, decision forests. Typically, data scientists start with one of these algorithms and then iterate through many different ones. Now, once you have the algorithm, you need to tune hyperparameters. So in this case, this is a forest algorithm. It uses the decision tree that you probably learned in your high school. These are the hyperparameters for this decision tree. Swati will go into a lot more detail on what these hyperparameters are. How do data scientists choose what these values should be? Typically, they start with some random numbers, and then they evaluate the model that's output using these hyperparameters and algorithm. And then they iterate by changing these hyperparameters. So here's an example of several different hyperparameters just for one particular algorithm, right? All this is very time-consuming process. Let's see how manual this process is. You start with the data set, you choose an algorithm, then you tune hyperparameters for that particular algorithm. You get a model, you evaluate that model with some test data to see whether that is performing to your expectations. You change the hyperparameters because you want a better accuracy, better performance. Now you go through a training process again. You get a different model. You evaluate it. You keep continuing with a different hyperparameter setter. You can go on and on with just hyperparameters because it's an infinite set, right? Now you're not done. You go back and say, hey, this hyperparameter set is not working, or training algorithm is not working for me. Let me try a different algorithm. So you choose training algorithm 2. You go through the same process again. Training algorithm 2 has a different hyperparameters. Right? So this is super tedious, repetitive, and manual. Right? Let's look at this process with one of popular machine learning frameworks called scikit-learn. Now, this is a really busy diagram. You don't need to go through what each of these are. But you start at the starting point, label the data, and you go to, let's say, SVM, and you try it out. It doesn't work. Then he says, oh, go to KNN, try it out, again with different hyperparameters. You wait until the model training is complete. You evaluate the model. You keep continuing, right? There got to be a better way. We know whenever there is repetitive task, machines can do better than humans. It got to be much simpler. Introducing automated machine learning. Automated machine learning is going to reduce the time it takes, and it's going to save a lot of time and money. The goal of automated machine learning is to give you a model much faster so that you can iterate much faster and work on things that you love. How does automated machine learning work? You start with the data set. You configure automated machine learning with a few parameters. For example, you can ask automated ML to say, do data pre-processing. Automated ML has capabilities where we can go and impute missing values if we have missing values in the data. Things like that. The output would be a high-quality machine learning model that you can use to deploy and use it for predictions. How does the user experience work? Typically, data scientists have a Python script. In this case, a Jupyter notebook, but you could use any Python IDEs like PyCharm. We support any Python IDE that you're familiar with. Bring the data set, configure the AutoML. For example, you could say, build a model that has up to 90% accuracy, right? So you set a constraint in your configuration setting. Then you submit that experiment, we call it experiment, to Automated ML. Automated ML intelligently generates combinations of algorithms and hyperparameters and iterates through multiple algorithms and hyperparameters. The output is set of models that gets evaluated, and you get a high-quality machine learning model. So all the iterations and evaluations that you had to do manually as a data scientist are simplified now. Now, how does the automated ML generate these algorithms and hyperparameters? Some of our competitors actually use just brute force. On the other hand, we use our own machine learning model that was trained on millions of experiments and use collaborative filtering and matrix factorization to intelligently recommend what is the next pipeline going to be. So automated ML generates a pipeline, which is an algorithm and hyperparameters, trains, looks at the performance, learns from it, generates the next one. It iterates until, let us say you said, oh, I need a 90% accuracy model. It iterates until it reaches a model that has 90% accurate. Now, the key thing here is the more you use the automated ML, since we learn from each of these, the better it gets. So over a time period, we believe automated ML will generate higher and higher quality models. With all this, we know data is really very sensitive for you, and you want to protect the data. Automated ML has no need to see the data. So we preserve and safeguard your data. With that, let me show you how this works in action. My machine went to sleep, but so this is a Jupyter notebook. I have a model that I built using automated machine learning, taking a handwritten digits that you just saw in the slides. What you would do is you would set up an Azure subscription and create an automated ML experiment. And also, automated ML is part of Azure Machine Learning, so it comes with an SDK that you would install and download. We have a setup script that installs this for you and sets up the environment, making it easy. In your Python notebook, you import the automated libraries, Azure Machine Learning and automated libraries. and give a name for experiment. I'll walk you through really the automated ML portion, right? You specify whether this is a classification task or regression task. We support both classification and regression. The metric is where you can specify which metric that you're wanting to optimize. For example, you can say if you're doing a classification, you can say, I want 90% accuracy, right? So we support few other parameters other than accuracy, like AUC weighted. We do the same for regression. You can specify how long you want your job to be, not to exceed. Continue this. This is where I'm getting the data set. This is the handwritten digits data set. This is the training data set. You'll see the training data here. These are the handwritten digits, and these are the labeled digits, right? This is what you feed into the machine learning system. Once I have the training data set, I configure the automated ML object, specify how many iterations I would like. If I have cross-validation, in this case, I'm saying I want 5-fold cross-validation. If you're familiar with data science, you probably know what cross-validation means. I say I want optimization on accuracy, right? I instantiate this object. Now, I train my model with just one line of code. Say, submit my experiment. Right? Because I have specified 20 iterations, it generated 20 different models. Now, this training takes a while, so I pre-run this model. 20 different iterations with different set of algorithms and different set of hyperparameters. You can see the first iteration here is using KNN, second one using decision tree, third one random forest, so on and on. And it's showing me for each of these iterations what the accuracy has been and what is the best so far, right? So it started with 0.931, somewhere along it keeps increasing. Now, I ran this 20 iterations on my local computer. So you have the ability to start your experiment on a local machine. Then when you want to scale it, because you want to run more iterations or you have compute-intensive job, then you can scale it to the cloud. And Swati will go into a lot more details on some of the cloud options. But run the same experiment with 200 iterations on a cloud machine. What you see here is the leaderboard, meaning this one is the top performing model with an accuracy of 0.983, right? This is the second best one. And you can actually see this while they are being executed in real time. So you can make decisions like if an algorithm is taking too long, you can cancel that particular iteration so that you're saving time. We also support, if you know, certain algorithms do not work well for your model or the data set, you can exclude those algorithms. Automated ML will exclude those so that you are not wasting time. This graph here shows the performance of each of these 200 models, right? So this one has 0.72275, right? So you get the visibility of each and every model that is generated by automated ML. We want to give you the flexibility and control so that you can make decisions on these models. Right? Once I have all the models to the accuracy that I like, I go and say, give me the best model. So I have one call. I can go and ask for, give me the hyperparameters for my best model, right? So this is where we're showing all the hyperparameters for that particular algorithm. You can also see for that particular model the confusion matrix. So the green dots are showing the true values were corrected predicted accurately. The ones here, for example, says 3, digit 3 was wrongly classified as 0 3 times. So the model, right, any machine learning model is not going to be completely accurate. If it is, then this probably something called overfitting, meaning you're training the model really just for that particular training set, right? It won't work really well when it comes to real world. So we give you a lot of visibility. Then with a few clicks, by the way, you can see this entire model metrics visualization on web also, in addition to the notebook, right? So you have lots of flexibility and control. Going back to the demo notebook, with few more, so this is my test data. I pick random 20 digits, and you can see this has classified few of them, many of them accurately, but this one, this 7, it classified as predicted as 2. Kind of see it does look like 2, but the model machine learning is not always accurate. If I run this again, it's taking the 0. This looks like 6, but classified as 0. You can see we give you the digits and the predicted values. With few more lines of code, you can actually deploy the model into Azure Kubernetes service. So we take the model and containerize it and deploy it in AKS. You can do all this using API. Now I have a web service that I deployed, the model that was generated here. Let me see how this works in real world. So I have a digit that I return, says 3, predicted accurately. Let me see whether I can do this with, let me take the most complicated. Happened, sorry. So I done 8. Let me save this file. And let me go back to my notebook. Let me run it and see whether it predicts. It did not save the file. Sorry, guys. Okay. As you can see, with just a few lines of code, you can build a machine learning model and deploy it and use it for your predictions. Now let me switch back to my presentation. Really, 2 lines. Configure your automated ML and run. Let us see how our customers are using automated ML. And I'll skip this just in the interest of time. We have BP, one of our marquee customers. Manish from BP is going to let you guys know how they're using automated ML and what they have seen, their experience on using automated ML. Manish? Technical difficulties, we have to reuse the mics, so bear with me.
Hello. Hi, everyone. My name is Manish Naik, and I work as a principal in a team called Digital Innovation in BP. So we've been working on the Microsoft version of Automated ML now for about 6 to 9 months. And I described this specific use case earlier, but as Krishna mentioned, there are 3 key benefits that we see in productionizing automated ML. First one being fairly obvious, that this is a significant productivity enhancement for data scientists. So we have very strong data scientists, and it's in our interest to ensure that they are productive. So model creation time, as described, could, depending on the use case, come down from days to hours. The second is, so data scientists are not going to immediately start trusting what automated machine learning suggests. So as they work in their existing fashion, they also run the models against automated ML. And the more comparable results they see, the more trust they will develop. And you can imagine building a robust benchmarking process where for every machine learning project, you would sort of exhaust the what-if scenario that data scientists have, which is, what if I tried this algorithm and that combination? Would that improve my accuracy? And that what-if scenario can be taken care of by the benchmarking process with automated ML. And lastly, we have a lot of domain experts in the company, like every other company, so heavily analytical folks, data-heavy folks who build models in Excel or MATLAB, haven't done Python programming, or people like me who don't have the time to code anymore, ex-Python programmers. I think this can, automated ML will leverage, will allow these domain experts to leverage machine learning without having to go through an extensive training process. It's still early days in our thinking here, but we think that we can allow these folks to experiment on their own, and within the Azure environment, pass on their results to the central data science team, perhaps, who could evaluate and productionize. So hopefully I was able to give you a glimpse of how we are planning to use automated ML and productionize it in BP. Thank you.
Thanks, Manish. We have seen other customers using automated ML and benefiting in many different ways. For example, here's a testimonial from one of the customers saying they spend a lot of time and they build lots of models, but they do not know when to stop and when they have a good enough model. With automated ML, it's helping them because it's providing the confidence that they need in model building. We have other customers using automated ML as the starting point, the model generated by automated ML as the starting point, and then tweaking it further to improve accuracy or performance. If you're a brand new data scientist, I have one from Novus data scientist that said he spent 4 weeks trying to build a model using SVM algorithm just to find out that SVM does not work for the data set. So they wasted 4 weeks, when in fact, if they had automated ML, they would have saved lots of time. I would like to invite Richard, our group program manager for Power BI, to show how automated ML is being used inside Power BI and help other personas enable the scenarios.
Can you hear me? You can hear me? Hey, so there wasn't a whole lot of code there, but there was still code. So what I want to do is show you.
He's seven.
What I want to do is show you how to do it, the same thing but with no code. How many people here know about Power BI? Use Power BI? Okay, enough.
Everyone.
So if you don't, this is what Power BI does for you. This thing right here turns your data into that. So on the left-hand side, you see the value of opportunities that have closed. On the right-hand side, this is a data set out of CRM, are open opportunities, and the revenue I'm going to earn from them. And what I want to predict is whether or not I'm going to actually win those opportunities. So that's setting up the contest. And to be able to do that, we've baked automated ML into the product, into Power BI. So the same thing you saw just now, can be done with a few clicks. And let me show you how. So I want to build a prediction. I click, instead of Jupyter, I click on this little brainy icon. I say create a machine learning model. It's a binary prediction or classification, so I click that. Next, I pick the table and the column that contains the value that I want to train on. For past opportunities, that's won or lost. For future opportunities, it's null. Click next. Pick the columns that I want to include in the model, where automated ML is going to look through those columns and determine whether or not there's information that's correlated with a won or lost opportunity, and then turn those into features. I'm just going to select everything and let automated ML do its trick, do its thing. Select next, a model name. And some labels for some reports. I click save. And that kicks off the same processing. So Power BI is now using automated ML to build the model. That will be applied to the data. And every time the data is brought into Power BI, that model is run on that and scores or it evaluates the likelihood of an opportunity when or closed. That's going to take a while, so I'm going to jump ahead to the a previous model I built. And so 82% accuracy, and I see my list of the features of the model. And the top one is incident count, and when the chart on the right updates, it's going to show that it's correlated. A low number of instances correlated with winning opportunities makes sense, right? You've got a customer has a lot of problems with your product in the past, I might think about you in the future, and you can. You can see the correlation there. You can also explore, I don't have time to go through each one, but you can also use this to explore your data and see how each of these fields influences. And then, if I'm happy, it's 82% accuracy, I'm happy, I'm going to apply the model, type in the column name, win confidence, and then I say apply, and it goes right into my model. It goes right back into my data. I go back to Power BI, I can now have the likelihood of all of my opportunities closing, and then I can now focus on, here's a sizable opportunity with a low confidence of winning. I can then, as a sales manager, I go talk to my salesperson, we go through the data and figure out what we need to do. So there you have it. Now you've seen automated ML work, and it's being abstracted away, and now the analysts can take advantage of this technology. Thank you.
Thank you, Richard. As you can see, automated ML is very powerful. Right now, we support classification and regression types of problems. Popular framework is scikit-learn and Python language, which is majority of data scientists use. Data types, any scikit-learn supported data, numericals or text, NumPy or pandas data frame. We also support local files. We have file in that you want to use for training and building a model. That's on local storage, and you can use the local computer to build a model, as well as cloud storage. For training your jobs, you can use local computer, as well as if you want to scale it up and scale it out, you can use the Azure cloud. It's available now, announced it on Monday. Go here and check it out, ak.ms/AML notebooks. We have lots of sample notebooks that you can use to get started. Now, if you're starting from scratch with just dataset, automated ML does algorithm and hyperparameter selection for you. If you already have an algorithm and want to do hyperparameter tuning, my teammate Swati will walk you through the hyperparameter tuning process. Thank you.
Thank you, Krishna. Good afternoon, everyone. In the previous part of the session, we saw just how complex the process of developing and tuning your machine learning models can be. In order to truly democratize machine learning, we need to have solutions that can automate this process of building and tuning your models. I'm Swati Gharse, a product manager on the Azure ML team at Microsoft, and I'll be presenting a new capability in Azure ML that allows you to automate the process of tuning hyperparameters for your model. Let's start with a recap of machine learning applications. These technologies today are revolutionizing a variety of industries. From automated machine translation that lets you speak in a foreign language when you're traveling abroad, to product recommendations that you see when you're shopping online on e-commerce sites, to image classification, and even self-driving cars. Chances are that regardless of the industry you work in, you can leverage machine learning technology to build models that'll help you better serve your customers. So what's the process of developing and training a machine learning model? What does that involve? You start out with a training data set, which is a set of labeled data for your domain. For example, if you're building an image classification model, this would include a set of images, each of which are labeled as belonging to a known category. And you feed this training data set along with the training algorithm. And at the end of your training process, you would have generated a model that you can use to make a real-world prediction. The training algorithm itself could be a simple traditional machine learning algorithm like linear regression, or you could decide to use a state-of-the-art deep learning algorithm. And depending on the kind of training algorithm you use, the generated model would end up being either a simple linear function, or you would end up with a deep neural network. Another factor that influences the performance of the model you generate is the parameters of the training algorithm itself. And we call these parameters the hyperparameters of your model. So hyperparameters are adjustable parameters that govern the training of your model. And you typically select these values before you start training your model. And these values stay constant throughout the training process. For example, when you're training a deep neural network, before you start your training, you will need to select hyperparameters like the number of hidden layers in your network, or the number of nodes in each layer. This would also include things like learning rate, which is a measure of how quickly your network abandons its old beliefs for new ones, and batch size, which tells you how many training samples you'll have in each iteration. Let us look at an example of actually building a model for image classification. You start with the training data set, which in this case is a set of labeled images, and each image is labeled with a category that that image belongs to. And you feed that training data with the training algorithm, and you have to select some values for your hyperparameters. In this case, let's say you have to select values for the number and size of your hidden layers and what learning rate you want to use. And at the end of your training process, you'll have a model where you can feed in any image. And for that image, the model will predict the class that image belongs to. Turns out that in machine learning and deep learning scenarios, the performance of your model depends heavily on the values of hyperparameters you selected. For example, when you're training a deep neural network, the values you use for the number of hidden layers could have a strong impact on the accuracy of the model. And using different values here for hidden layers would end up in models with vastly different accuracy. In this illustration, we see that using one hidden layer in your network would end up in a model that inaccurately classifies this image as a bird, but using two hidden layers correctly classifies that same image as an airplane. In reality, only a small set of hyperparameter values end up performing well, while the vast majority end up performing quite poorly. So the goal of hyperparameter exploration then is to search across the space of all possible hyperparameter values and come up with a configuration that gives you good performance. For example, when you're training a neural network, you might want to try different values for number of layers and for the learning rate. And you might want to try a network that uses 2, 4, or 8 layers, but the learning rate could be anywhere between 0 and 1. And you want to vary these parameters in such a way that you optimize for a model that results in the best accuracy. Turns out that there are several challenges in doing this. First of all, the space of hyperparameter values is quite large. That is because you might want to tune a large number of hyperparameters, and each hyperparameter can take on several different values. There's also a sparsity of good configurations, which is to say that only a small set of these values end up performing well, while the vast majority actually end up performing quite poorly. And evaluating each of these configurations is quite expensive. It takes up a lot of time and resources to go through a set of hyperparameters and see how your model performed. Given that we all have limited time and resources on hand, we would want the most efficient way to find the right set of hyperparameters for our model. The typical process when you already have a training algorithm and want to tune the hyperparameters, it's painstakingly manual and just not scalable, right? You already have a training algorithm here. You would typically start with picking some configuration of hyperparameter values. You'd randomly pick some set. And you take it through the training process, at the end of which you generate a model, you observe how this model performs, and then you manually go back and iterate over this process over and over and over again until you find a model that performs well. There are several problems with doing this manually. First of all, as you can imagine, doing this iterative process over and over again manually can be really, really cumbersome. Secondly, it's pretty hard and almost impossible to come up with good values that perform well early on in your exploration. And finally, for the vast majority of values you try, they would end up performing poorly, and you would end up wasting significant time and resources exploring those values. Wouldn't it be great if instead we could have a way to automatically tune the hyperparameters for your model? The new capability that we announced in Azure-ML this week lets you do exactly that. It allows you to automate the process of exploring your hyperparameters, and does this in an efficient manner, saving you significant time and resources. In addition, it lets you optimize the model for a specified metric. Like, let's say you want to find a model with the best accuracy. It lets you control the resources you spend on this exploration. So you can specify the maximum amount of time you want to spend, or the amount of compute in terms of how many runs you want to spend on this exploration. And because it applies to different models and learning domains, you can use it regardless of whether you're using traditional machine learning or deep learning algorithms. It's also training framework agnostic, which means you can use it with TensorFlow, with Onyx, PyTorch, or any other framework of your choice. And finally, you have a way to visualize all these different configurations in one place, so your data scientists can go and decide which configuration performed the best for them. How does this all work? At its very core, hyperparameter tuning works by launching multiple training runs in parallel. And each training run explores a unique configuration of hyperparameter values. When a run completes, the same resource is now used to explore another configuration of values. And this process continues until you have exhausted all your budget. Behind the scenes, your hyperparameter tuning service needs to solve two main problems. First of all, how should it generate new runs? Meaning, how should it find the configuration to go and evaluate next? And secondly, given a set of active runs, how long should those runs execute? Should it allow each run to complete all the way through the end? Or should it instead terminate a run early? And if so, when exactly should it do that? In order to generate new runs, the user calls out which hyperparameters they want to tune. And for each hyperparameter, they call out the range of values that that hyperparameter can take. They also specify a sampling algorithm, which is used then to pick samples from this defined space. And these are the configurations that Azure ML will try for you. So we support a variety of different sampling algorithms. You could use grid sampling, which in a sense is an exhaustive search over all feasible values in the hyperparameter space. You could use random sampling, which randomly picks configurations from your defined space and explores those for you. And you could also use Bayesian optimization-based sampling, which makes intelligent choices about which configuration to try out next. It basically picks the next sample based on how previous samples have performed in such a way that the next sample will improve your reported metric. It makes trade-offs between exploiting a known good region of the hyperparameter space and exploring a lesser known region. You can think of this as being similar to a choice you make when you say, pick a movie genre to watch, right? Should you go out with the usual genre, which you know will be reliably good, or should you take a risk and try something completely different, which could prove to be great, or also stands the risk of being quite terrible? So let's suppose for a moment that one of the configurations you tried out did not perform well. If we allowed such a configuration to run all the way through the end, we would end up wasting significant time and resources. Instead, if we had a mechanism to terminate such a run early, we would be able to leverage that freed up resource and use it instead to try out a different configuration. And Azure ML lets you do exactly that. We evaluate each of your training runs for a specified metric. Of course, your training script will need to report this metric to Azure ML. And based on some criteria that you specify for early stopping, Azure ML will automatically end a poorly performing run early for you. So you see in the highlighted section of the graph, the runs that were performing poorly were ended early for you, while the runs on the top section, which were performing quite well, completed all the way through the end. And doing this early termination saves us significant time and resources. We'll see that in a demo as well. So you need to specify which configuration to use for early stopping, and we support a few different options here. You could use the bandit policy, where you come and specify a slack factor, let's say 10%, and every time Azure ML makes a decision for you, any runs that are not within this allowable slack factor, which are not within 10% of the best performing run, they'll be early stopped for you. You could use median stopping policy, which computes a running average of the primary metric for all runs, and then any runs that are performing worse than the median are stopped early. And you could use truncation selection, where you specify a certain percentage, and then each time Azure ML, it early terminates the lowest performing X% of runs for you. And all of this is done automatically. Also, if you're new to the whole process and you don't know what kind of early stopping to use, Azure ML will apply the median stopping policy by default for you with certain known values. Because in our tests, we've seen that using this policy, it's quite conservative. It saves us 25 to 35% resources without giving up on any accuracy. So by default, we would apply that if you don't select one. In order to use Azure ML for tuning hyperparameters, the user needs to specify some inputs. Of course, you call out which hyperparameters you want to tune in the first place. And for each hyperparameter, you call out the range of values it can take. You specify a metric to optimize, like let's say you want to maximize the accuracy of your model. And you can call out an early termination policy, which is what will give you that savings. And then you specify the budget in terms of how much maximum time you want to spend on your exploration or how much compute in terms of how many runs. And you provide your training script and training data. You bring your own data here and submit an experiment in Azure ML. And at the end of this hyperparameter tuning process, Azure ML will tell you the recommended configuration and tell you, the actual values of hyperparameters that ended up performing best. And it'll tell you how each of the different tries that it tried out, how those performed. We'll take a look at how you can do this in a quick demo as well. Switch to 6. So in this demo, we'll use the Azure ML SDK to tune the hyperparameters for an image classification model. And we'll do this all using the Jupyter Notebook. But you can use any IDE of your choice. Because it's an image classification model, you start with the training data set, which is a set of images. We're using the CIFAR10 data set, a standard data set of images, where each image is classified and labeled with a known category, like you have pictures of airplanes, birds, cats, and so on. And to start off, we'll set up a workspace, which is the top-level resource in Azure ML. And you create an Azure ML experiment, which is a container for all the different runs that we try for you. Next thing you'll have to think about is the compute target that you're going to use for training. It turns out that the process of training a model can be quite compute intensive. And Azure's Batch AI service allows you to leverage the power of CPU-enabled and GPU-enabled VMs that you can use in your training. In this case, because we're building an image classification model using deep learning, we'll want to leverage a GPU-enabled VM. And you can specify this type of VM and the size to use in here. We use a standard NC6, which is a GPU, which has like one NVIDIA GPU in that VM. And Azure also allows you to configure the size of the cluster. That's how many nodes do you need in your training. Out here, we leverage the auto-scaling functionality of Batch AI, where the size of your cluster automatically grows on an as-needed basis. So because we want to try out 10 runs in parallel, we say that use a maximum of 10 nodes in our cluster. And we set the minimum nodes to 0, which along with auto-scaling, ensures that when all our training runs are done, it automatically deletes these nodes for you. So that will ensure that you don't incur any additional costs when you're done with your tuning and with your exploration. So we have our, is that a question?
Does that guarantee me 10 parallel nodes?
Yes.
Could I end up with like 6?
So there is a quota that is typically controlled at the Azure subscription level. And if you and your teammates are sharing a particular subscription, you'll want to ensure that there's enough quota under that subscription for all of you to have the nodes you're asking for. But assuming you have the quota, that will guarantee that your jobs have 10 nodes. Okay. I'm sorry?
So it's not scaling, basically. It's just using 10, not like...
No, it actually does scale. So if you look at your bill, you will notice that it uses up to 10 based on how many jobs you want. You're running. But for example, let's say you need 10, but your quota does not allow that. That was the thing I was calling out. But the scaling is for real. So while your jobs are running, if you have 10 jobs running in parallel, it'll scale up 10 nodes in that cluster. When you're done, you'll see that if you go into the portal, you'll notice that the cluster goes down to 0 nodes. So next, you'll need your training script, because here you have your training algorithm, and you were using Azure ML for tuning hyperparameters. And you could use any script you like, with the only caveat that your script needs to report that primary metric back to Azure, right? And you could use this one line that you add into your training script to ensure that that training script logs back that primary metric. In our case, we are trying to optimize for accuracy. So if you add this line, then you will be reporting accuracy metrics back to Azure. So you copy your script over and upload the training data to the cloud. And you create an estimator that you will use in your training, which is a high-level abstraction that allows you to train in the Azure ecosystem. And it's in this estimator that you specify which training script to use and which compute target, any other Python packages that your script might rely on. And next, we'll focus on the part where you configure the hyperparameters for your experiment. So we call out, first of all, which hyperparameters we want to tune. In this case, we're going to tune 4 different hyperparameters: the initial learning rate, the learning rate decay, the momentum, and batch size. And for each of these, we call out the range of values they can take. The hyperparameters themselves could be discrete or continuous. Like batch size, I call out a specific set of sizes to try. Whereas for the other parameters, I just specify a range and say it's a uniform distribution between 0 and 1, or whatever my values I want to try are. And because I'm using random sampling, Azure ML will pick samples at random from this defined space and try those out. Next, I look at my early stopping policy. This is what's going to give us the savings. And I decide to use bandit policy with a slack factor of 0.1, which means that any runs which are not within 10% of the best performing run, those would be early terminated. And I call out here the primary metric I want to optimize for. So I'm saying I want to maximize the accuracy of my generated model. I also specify the budget. In this example, I'm keeping it simple. I'll run just 20 runs in total, and I'll run 10 runs at a time. And once I've set up all this config, I go and submit the experiment. In this case, because I'm using a deep learning algorithm, each training run can take up to 5 to 6 hours. So we won't wait here waiting for that to complete. We'll instead load up a previous experiment that I submitted using the same configuration that's completed, and we'll see what Azure ML has done for you. So I load up a previous run, and I want to call out a few things here. It used the same configuration where I ran a total of 20 runs, running 10 at a time. And the first thing I want to show is the duration of the experiment. This entire tuning experiment completed in 9.5 hours, which, if we compare with the manual process, right, where a data scientist would try one configuration, wait 5 to 6 hours for that to complete, and then iterate over that, you would typically have a user being able to explore only 2 runs every day, and exploring 20 different runs would take them 10 days right there. And using Azure ML, we've cut that time down to 9.5 hours, even for a long-running experiment. The next thing I want to call out is these completed versus canceled runs. Of the 20 runs we tried out, 10 of them completed all the way through the end, and another 10 were canceled early in the exploration process. And this is because Azure ML automatically early terminated poor performing runs based on our bandit policy. So half of these runs were stopped early, and if you look at how long each of those runs ran, you'll see that many of the early stopped runs were in this region. They were stopped in the runs here. They were stopped in the first hour or so of this exploration. So if you go back to the duration of each run and add it up, that's this column here, over the 20 runs, you'll see that you spent a total of around 60 hours of compute exploring all of this. Compare this again with the manual scenario, where each run was taking 5 to 6 hours, and you tried 20 different configurations. You would have easily spent around 100 to 120 hours of compute time trying this out. And because of the smart early termination that Azure ML lets you use, you ended up using only 60 hours, compute hours. And this is the visualization I was talking about, where you can see all the different 20 runs. And you could do this with 100 runs. There's really no limit on how many you can try out. But you can see here that the runs in this region that were performing poorly as compared to the better performing runs, these were early terminated. And you saved significant time and resources by not getting those through to the end. And the runs in this region, which were performing well, were allowed to complete. There's also another cool visualization that we offer, which is called the parallel coordinates chart. And this allows your users to visually correlate the impact of individual hyperparameters on your performance metric. So each axis here corresponds to a different hyperparameter. Let's take a look at momentum, this axis. And you have yellow lines, which represent configurations that performed well, and purple lines that did not do so well. And if you look at this, it's easy to tell that values for momentum in the upper part of the range perform quite poorly, while values in this region ended up with yellow lines performing quite well. And this is important for your data scientists who might want to look at this data and iterate over the experiment again and decide what set of values to use next. You can also see similar visualization in the portal, by the way, in case you're not using a notebook. This is the same experiment pulled up in the Azure portal, and you can see how the different runs performed. Coming back to our notebook, let's see what we can do with this experiment now that it's completed. So we had Azure-ML find us the best configuration. We can use the getBestRun by primary metric method and find out the actual values of hyperparameters that were used for this best configuration. And so it shows us that for each of our 4 hyperparameters that we were trying out, these were the values that resulted in the best performance. And once we have that best run, we can easily go and register a model from that best run. Once we've registered this model, it's fairly straightforward to deploy an Azure service that uses this model for scoring real-world images. So I'll go over that really quickly. In order to do that, you'll need a scoring script that you can use. And you create a container image that calls out which scoring script to use, any Python packages that your scoring script depends on, and you point to the model that you just registered from your best run, and create a container image with that. And then you can deploy an ACI service, an Azure service, that would give you an endpoint that you can now call with any real-world image. So let's try out this model that I've already deployed in an existing service. We know how the internet loves images of cute kittens, right? So let's take this image, take the URL to this image, and it's the same URL I have put in here. And then I call the ACI service, the Azure service, that was scoring using the model from my best run. And I run it. And you can see here, that it returned the classification of that image. It returns the probability of this image belonging to each of the 10 different categories of my training data. And if you look at the category with the highest probability, it tells me that that image was that of a cat. So it's fairly straightforward to start with some training algorithm. You could either use something that you built yourself, or your teammate provided you, or you found somewhere else, and easily control how you tune the hyperparameters using that model. And once you have a model, it's fairly straightforward to deploy a service using this model for real-world predictions. To conclude, I would say that this new capability in Azure-ML really makes life easy for your data scientists by automating the process of hyperparameter tuning. And it does this in an efficient manner, saving significant time and resources. Yep, so this capability is available now. It's available in preview as of this week. You can try it for free over here. We can't wait to hear your feedback. And if you guys are interested in other offerings from Azure-ML, there's a list of other presentations we have lined up this week at Ignite that you might find interesting. With that, we might have a few minutes for questions if you guys have any. All right, thank you all for coming.